Next, we have a look at water. Now, water is made up of 2 hydrogens and 1 oxygen. So if we have a look at oxygen's valence electron structure, we know oxygen is in group 6, and so it has 2 electrons that don't have partners. And this is where a hydrogen joins on, and there's a shared pair of electrons there, and then another hydrogen joins on, and there's a shared pair of electrons there. Oxygen has 2 lone pairs. Now, I want you to think of the lone pairs as taking up a lot of space. And so because they take up space, that hydrogen can't be repelled by that hydrogen. So it can't move out and become a linear molecule. These lone pairs are in the way. And so water we call an angular molecule. Now, if we look at the individual bond between the hydrogen and the oxygen has an electronegativity of 3.5. The hydrogen has an electronegativity of 2.1. So the oxygen, therefore, has a stronger pull on the electrons. So remember what we must do. We take the 3.5 minus the 2.1. So the electronegativity difference is 1.4. If it isn't 0, then we know that this bond over here is a polar covalent bond. And because oxygen has a stronger electronegativity, then the electrons are still shared, but it's an unequal sharing of electrons. And then the same happens with this hydrogen-oxygen bond. So each individual bond is a polar covalent bond. Now the oxygen, because it has the higher electronegativity, becomes slightly negative, and the hydrogen becomes slightly positive. And now, because of this, if we have a look at this molecule, there's an unequal distribution of charge. You can think of the electrons being closer this way, so there's a density of electron cloud around this way and less around the hydrogens over here. So overall, as a molecule, it is also a polar molecule. If we have a look at the Cooper notation, that line there represents the shared pair of electrons between that hydrogen and oxygen, and over here the other shared pair of electrons. So this shape is called angular. There are individual polar covalent bonds between the hydrogen and oxygen. There's an unequal distribution of charge because of the unequal sharing of electrons, and it forms a polar molecule, and another name for a polar molecule is a dipole. Next, we are going to have a look at ammonia, NH3. And if we look down here at the Lewis diagram, we know that nitrogen is in group 5. So it's 1, 2, 3, 4, 5. We can see that 3 of the valence electrons don't have partners. There's this one lone pair. If you have a look over here, the lone pair takes up a lot of space. And so essentially what it does is it makes sure that these hydrogens can't push up and become a flat molecule. Because there's a lone pair there, we can see that the shape of this molecule, it looks like a little pyramid. And so this shape is called a pyramidal molecule. Now you can see the hydrogen joins on in each of these places, and so nitrogen has 3 shared pair of electrons and each hydrogen has 1. And so if we represent it with Cooper notation, the hydrogen is bonding 3 separate times to a hydrogen, and then we have that lone pair. Now if we look at the electronegativity, the nitrogen has an electronegativity of 3, and the hydrogen has an electronegativity of 2.1. So if we look at the difference, it's 3 minus 2.1, so the difference is 0.9. So as soon as the difference is above 0, we know that the bond is a polar covalent bond. So what happens is the nitrogen becomes slightly negative because the electrons are unequally shared and they're closer to the nitrogen. So the hydrogen then becomes slightly positive, and the same happens in each of these 3 bonds. Now, because the lone pair takes up so much space, it pushes the hydrogens down, so we don't have this flat molecule, and then it forms this pyramidal molecule. Now, because there's a concentration of the positives down here and a concentration of the negative up here, you can see this is showing you the density of the charge, and we can see this is an asymmetrical shape. So as soon as we have an asymmetrical shape, we make a polar molecule, which is called a dipole. So each individual bond is a polar covalent bond, and the overall molecule is polar because of the distribution of charge. So this shape is a pyramidal molecule. There's an asymmetrical distribution of charge in the molecule. It's a polar covalent bond between the nitrogen and the hydrogen, and the result is a polar molecule, and another name for a polar molecule is a dipole. Carbon tetrachloride is an example where we have a central carbon, and what happens is each of the unpaired valence electrons from the carbon shares with a chlorine, because remember, chlorine has 3 lone pairs and it only has 1 that needs a partner. So 4 chlorines join on, and this type of molecule where you have 1 central with 4 added on, this is called a tetrahedral shaped molecule. Now, if we have a look at the carbon, it has an electronegativity of 2.5, and chlorine has an electronegativity of 3. So the electronegativity difference is 0.5. It's not 0. So it means each of these carbon-chlorine bonds is a polar covalent bond. Because chlorine has the higher electronegativity, the shared pair of electrons are closer to the chlorine, so it becomes slightly negative, and that happens for each of the chlorines. So each individual bond is a polar covalent bond. Now, if we look at the Cooper notation, you can see there's a single bond from the chlorine, and then the carbon is bonding to 4 chlorines. Now, because of the layout of this molecule, the chlorine pulls this way and then it pulls that way. Then the chlorine pulls this way and that way. And because of the special layout of this molecule and its chlorine on all 4 parts there, it means that the charge distribution becomes symmetrical. So each carbon to chlorine bond is a polar covalent bond, but there is an overall symmetrical distribution of charge in this molecule. And so the overall molecule is a non-polar molecule, with the individual bond being a polar covalent bond. At this point, I want to show you what this SAGS document says about chemical bonding and intramolecular forces. I've only pasted the part that is relevant to the covalent bonds. We're still going to go on to ionic bonds. So you define an intramolecular bond as a bond which occurs between atoms within molecules. Then you define a covalent bond as a sharing of at least 1 pair of electrons by 2 nonmetal atoms. Then the nonpolar covalent bond, also known as a pure covalent bond, as an equal sharing of electrons, whereas the polar covalent bond has an unequal sharing of electrons, leading to a dipole forming as a result of an electronegativity difference. Then you define electronegativity as a measure of the tendency of an atom to attract a bonding pair of electrons. Then you must be able to use electronegativity numbers to determine the specific type of covalent bond. A zero difference in electronegativity indicates a non-polar or pure covalent bond, and a non-zero difference in electronegativity indicates a polar covalent bond. The greater the difference in electronegativity, the more polar the bond.